notes, not the notes, excuse me. These are the answers for Wednesday's quiz. So problem 1a, with this function, when you add 2 on the inside of the function, what that does is it ends up shifting your function 2 to the left. And then when you add the 3 on the outside of the f of, it's going to end up shifting your function 3 up, which then, if this is a point on the original graph, so if this was a point on f of x, then a point that'll work in this new function is going to get shifted 2 to the left, so it would be negative 19, and it's going to be shifted up 3, so then it would be positive 14. Here in 2a, when you take your function and every output of your function gets multiplied by 2, you're going to end up stretching vertically. So this is going to get stretched up and down vertically. By a factor of 2. Here, the input here, what's going in, first thing that happens is it gets multiplied by 1/3. So one way to think about this is that you need to put in something 3 times as big to get back to the same place that regular f of x. Right? So if you're comparing this one to regular f of x, you need to put in something 3 times as big here in order to do the same thing that f of x did. So what happens with this one is your graph gets stretched, elongated, pulled out horizontally. So this gets stretched horizontally by a factor of 3. These two problems here are probably the most difficult ones on this quiz. Quickly, well actually here, we're going to do this. I'm going to skip 2 pages ahead and we'll take a little detour and talk about what's going on with these functions. So if you want to compare, we'll start with something, we'll do an example here. Set ourselves up for problem 3. So if you want to compare f of x to, we're going to compare it to something very easy to understand, f of x plus 1. And if we know that the point a comma b works in this function, right? So if I put in a, I get out b. We can draw ourselves a little function machine here. And we have no idea what f of x is doing. It can be multiplying our input by 7 and then dividing that by 3 and then squaring it all and blah, 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 blah. So there's whatever goes on in the inside here, we're clueless about. But we do know that if I take and I put an a value in to this function, whatever it is, a b value will spit out, right? So that's what this is saying here. So now over here in this example, if we're looking at what happens to f of x plus 1, well, you can think about it this way. If I take and I put in to the function an a, well, that a then is going to become, all of that then becomes b, and then I'm going to immediately add 1 to that. Right? So what started as an a became turned into a b, and then I added 1 to it. So if the point AB works in this function, then that would mean that over here the point A comma comma b plus 1 would work in this new function. Right? So it's pretty easy to see. You put in the same old a, you get a b, and then something else happens after that. After the function does its work, we're adding 1. So this is one example of things that happen after the fact. So here's another example, right? Make it a little more complicated. You do 3 times the function plus 1. And again, let's watch what happens. If I plug in a here, and then when that a gets plugged into this function, right? So it's this machine over here that somebody's built. We have no clue what's going on the inside, but I do know whenever I put an a into it, a b will spit out. So over here I put in an a, then all of this here becomes a b. And then what happens to that b is it gets multiplied by 3, and then all of that we add 1 to it. So then the end result is that when I put in an a, I get out a b times 3 plus 1, or 3b plus 1. So that's the first example. This is the example of changing things after they spit out of the function. Right? Second example we can look at is what happens when you change things before they get plopped into the function. So again, right, so here we go. Second example, we're now trying to figure out what's going on before, when you change things before you put them into the function. So we have our original function, f of x. We know that if we have an a and a b, we know that we have an a and a b, right? So the a goes in and a b comes out. So again, we have no clue as to what's going on the inside here. Clueless. We just know that when we plop an a into the function, absolutely reliably a b comes out. So now let's look what happens if we have, again, we'll just make this reasonably straightforward. What happens if we have something like this, where we've got an f of x minus 1? And the way you can think about this is that before the function starts doing its work, we have a little filter, right? So we have our function. We don't know exactly what this function does. It could be cubing things, it could be taking square roots, it could be a step function, we don't know. But we've got some sort of filter, this filter that we've built on it, which is going to take whatever the x is and then subtract 1 from it. Now, if we could, after all of this happens, if this could become an a, right, that's an a, then that a drops into this function, and I know anytime I drop an a into the function, out spits a b. Right? So let's try this. Let's take, and instead of plopping an a in here and then getting a minus 1, and then not having any clue as to what happens to an a minus 1 when it gets dropped into here, let's take and let's put right into here an a plus 1. So I'm modifying what I put in to the function because I know that I have this filter on it. So if I put an a plus 1, the first thing that happens is the filter strips off 1, right? Subtracts 1, which then makes a plus 1 minus 1 becomes a. The a drops into the function machine, and just like clockwork, out pops the b, which then means we can say that this function is going to have a value a plus 1. We know that the point a plus 1, if the x-coordinate is a plus 1, then the y-coordinate is going to be b. Right? So here's one sort of our starting example about how the input changes and what that looks like in terms of points that work in the function. Right? So again, if a comma b works here, then a plus 1b works in this function. Right? Here's our second example. complicated, but same concept. We're going to do 2x minus 1. And you can think about this as being a filter on top of this function. We don't know exactly what's going on the inside of the function, but we do know that when we plop a in, we get b out, right? So we'll draw this. So we've got a 2x minus 1. We got the function machine here ready to do its thing. Have no clue as to how it works, but we do know that if we can get an a in, then we get a b out. So now the trick over here is, can we get all of this to become a? Is it possible to make 2x minus 1 equal a? What would we have to plug in for x in order to get out an a? And then this is just a simple algebraic equation that we're solving. We add 1 to both sides and divide both sides by 2, and we get x is equal to a plus 1 divided by 2. Right? And that's just what we just figured out, is that for this function, if I plop in, if I start with a plus 1 divided by 2 as my x-coordinate, I will get b as my y-coordinate. All right? So now, that being the case, let's look at the first of those two problems on the quiz. All right? So this is problem 3a. And for problem 3a, again, we're comparing this function machine. I don't know what it is. I do know that the point AB is on the function machine, right? So we could again draw this little machine. Don't know what's going on the inside. I put an A into it. Out comes a B. All right? So this is what was on the quiz. Y minus 7 is equal to f of, right? So there's that function machine over here that when we plop an a in, we get a b out. But this time the filter on it is minus x. Now this might be easier for you to see what's going on, is if you write it as y equals blah 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 blah, right? So the y equals is your new function, and the new function is defined by, we're going to take this old function, we're going to plug in the opposite of x, and then we're going to add 7 to it, right? So again, sort of thinking about what happens, we'll do on the tail end, we're gonna get to be b, right? So then when we're all done on the tail end of this, what's going to spit out of our function is this b plus 7. So we know that the y-coordinate of this new function is going to be b plus 7, and now I've just got to plug in through the filter something so that when it comes out the other side of the filter, again, we have here this sort of minus x filter. I want it to transform whatever I give it into a, so that that a drops into this function machine, unknown operation on the inside, but it'll spit out a b, and then we take that b and we but we add a 7 to it, which gets us the b plus 7. And the way that we're going to get this to become positive a is we're going to plug in a negative a, which would then mean that this point, negative a for my x-coordinate, b plus 7 for my y-coordinate, will work in this function if a comma b works in this original function, right? And then the problem 3b, right? So again, we have some function. Now this time I've told you what the function is, right? So this function is the square root function, right? So we're looking at what happens here with the square root function. Now the square root function, again, we have this point a comma b that works here, right? So the other way to say that is if we take the x and plug it in, we would take the square root of that, and that's going to give us b. Right? So a comma b working in this function means that the square root of a is equal to b. Right? So now watch what we can do with this. Again, thinking about what happens, what's the filter before it gets to the function, and then what happens after it comes out the other side of the function. So we're starting with this. We have the 3 times the square root of, right? So this whole square root of stuff, that's the function. And this is the filter, 2 times the quantity x plus 1. And then after we're all done, here, we'll tidy this up a little bit here. After we're all done, we're going to, after the function's all done, we're going to multiply whatever comes out by 3, and then we're going to subtract 4. Right? So first thing we can do here is we can think about this in the following way. Okay, you're going to have to bear with me for a second as I set this up. Actually, hold on a second. Alright, so now it's been set up. So I've purposely covered up all of that was inside this square root function, because I know that if I can make whatever's under here, if I can make all of that into an a, then all of this, the square root of a, becomes, right, so all of this would then be b. And what the output would be, the y value of this would then be 3b minus 4. So I know what the output is going to be. This spits out as b, and it gets multiplied by 3, and then we're subtracting 4. Right? So now the trick is that I need to get what's under the square root symbol, like what's inside this function, to be a. And we do that. Right, so let me just sort of, can I do this? Yeah, there it is. So we reveal this again, and again the goal is to get all of this, to get the, let's see, we'll put it down over here. Get nope. Excuse me for a minute. Back. Trying to color code here. To get the 2, to get the filter, 2x plus 1, I want to get that to be a, which means that I want x plus 1 to be equal to a over 2, which means that the x that I'm going to plop into this thing is going to be a over 2 minus 1. Right? So we're going to take, right, so it's going to be a over 2 minus 1, so that when I plop this in, right, the a over 2 minus 1 gets 1 added to it, which makes it a over 2, and then it gets multiplied by 2, which makes it a, which then makes the square root of a b, and then what spits out is 3b minus 4. So end of the day, if a comma b works over here, then a over 2 minus 1 works for this function. Right? So you probably forgot, but we were doing all of this because we wanted to, I'm trying to go back to the beginning here, get the answers to the quiz that you took on Wednesday. Right? So we just finished question 3, and now I can go on to question 4 here. Right? This one's a little more straightforward. Right? So this is my function. This is my y right here. And if I'm going to take the inverse, I'm going to take everything that was a y and make it into an x, make everything that was an x into a y. So the inverse is going to be x equals negative 2, y minus 1, the quantity squared plus 4 with a domain of x greater, we're switching all of the x's into y's, and we're switching all of the y's into x's. So then this x would end up becoming a y. So then the y is going to end up being greater than or equal to 1. And then we're going to solve this and write it in y equals form. So get the y to be all alone. So that means that we're going to have to subtract 4, right? So we had an add plus 4. We subtract 4 from both sides. And then we divide both sides by -2. I'm going to put the negative up here and then divide by 2, which is then going to leave me with y minus 1, the quantity squared. And then I'm going to take the square root of that, which is going to give me the square root of, and I'm going to multiply through the negative so that I get a 4 minus x all divided by 2, and this is all inside the square root symbol, and this is going to be equal to y minus 1. And then I'm going to add 1 to both sides. Actually, we'll save ourselves a little room and do it this way. Right. So we ended up adding 1 to both sides. So we get over here on the left side plus 1, and we get our y here. And this is our function. We know that its range is going to be y greater than or equal to 1. And then the domain of this function, you know that in order to get y to be greater than or equal to 1, actually if you look at the function, it makes sense that the domain would have to be y greater than or equal to 1, because this over here, everything underneath the square root symbol, is never, the square root, it will never become negative. Right? So the smallest that this could ever be would be 0, and then that would make your y equal to 1. And anything you plug in here is going to become larger. It's going to be 1 plus something here. And then the domain here, we know we don't want to have a negative sign on the inside of the square root. If x is 4, then 4 minus 4 is 0, and then 0 divided by 2 is 0. Square root of 0 is 0. That's fine. But anything bigger than 4, you're going to end up with a negative inside your square root. So the domain of this is going to have to be x is less than or equal to 4. Now, over here, if we look at this visually, again, if you're taking the inverse, you're putting in for you the y equals x line here, and then we're flipping this, reflecting it over the y equals x line. You can do it point by point. One of the points is going to be 4, 1 here. This point here, which is going to be 2.414, is going to be right up over here, and you're going to end up with something that looks like, oops, I missed. That's better. Something that looks like that, and it'll go through that point right there. Right. It's got a little bit more of a curve to it there. Okay. So in blue is a sketch of the inverse. All right, last problem. Okay, so you've read the problem, you've struggled with the problem. We know that from here down across the bottom and up is 60 centimeters. I don't know what S is, but if this is S, that's S, then that makes this down here 60 minus 2S. So that is the base, one of the bases of your trapezoid. Right? So one of the bases of your trapezoid is 60 minus 2S. then we got to figure out what this other base is up here of your trapezoid. Right, so we're looking for this base here. If you draw, that's not quite. I'm going to try that again because that's kind of ugly. Alright, see if I can do this better. If we draw that's a little better. This is supposed to be a segment, and it's a right segment. Then that also makes this down here a right angle. So if this is 90 degrees, that makes this right in here 30 degrees. If this is a 30-degree right triangle, then it's a special right triangle, and we know that the short side is half the hypotenuse, which makes this, actually I'll put it in here, makes this 1/2 s. And then we have another triangle over here which is identical. This is 1/2 s. And then the height of this, and you can go and remind yourself about the sides of a 30-60 right triangle, but the height of this is going to be √3/2 times s. And then that makes our base, the top base here, into, well, from here to here is 60 minus 2s. This is a 1/2 an s, that's a 1/2 an s. So it's 60 minus 2s plus a 1/2 an s plus a 1/2 an s. So the entire base across the top base is 60 minus 1s. Therefore, the trapezoid area, right? So the trapezoid area is going to be equal to, and we're using the formula that was given, it's going to be equal to 1/2 the height. The height is √3/2 times s, right? So 1/2 √3/2 times s, and then this is all going to get multiplied by the first base plus the second base. So this is 60 plus 60, which is 120, minus 2s minus 1s, which is minus 3s. So this is the trapezoid area. And here's the tricky part. The trapezoid area is, because this 60, original 60, is in centimeters, then that means that the trapezoid area, we'll do this in, do this in yellow. The trapezoid area, I said I'd do it in yellow, but I'm not. I'm doing it in blue. Trapezoid area is in centimeters squared. So if we want to get the volume, so the volume then is the area of the trapezoid, 10, but we're working in centimeters, so 100 centimeters in 1 meter, so this is going to end up being 1,000. Volume is equal to 1,000 centimeters, right? The length of the gutter times all of this, which is, well, at this point it's just simply a matter of cleaning up the algebra, and any form that you leave this in after this is perfectly fine. This, you could write this as 250, this is probably the cleanest form, times the square root of 3. Oops, there's an s right there. Times the square root of 3 times s times the quantity, 120 minus 3s. And we're done.